Key discoveries of the James Webb Space Telescope have subverted the case for the huge explosion. The James Webb Space Telescope has quite recently conveyed an exhilarating discovery that is sending shock waves through the universe of physical science. Through a single stunning picture, it has annihilated well-established debates, leaving researchers dazed. The time of hypothesis is over, as Webb's most recent capture is both outwardly dazzling and a distinct advantage that vows to change our view of the real world. What blazing discussion among researchers has this picture definitively finished? In what ways is the dazzling picture caught by the James Webb Space Telescope reclassifying our comprehension of the universe? Go along with us as we see the reason why it's getting awful, as James Webb's tracking down closes the discussion in physical science with a breaking blow. The crucial issue with astronomy is that researchers can't come to an understanding about how old the universe is or the way that quick it is extending. This unanswered peculiarity has confused researchers across ages, and they are directing different explorations to find answers. Cosmology is the field of examination that spotlights on understanding how the universe was made, the way things are assembled, and how it has changed over the long haul and eventually will end. This field has seen huge advancement in the beyond 100 years. The presently acknowledged cosmology model, the theory of how things came to be, suggests that the universe has been growing from an extremely hot and thick starting state for around 13.8 billion years. This expansion is estimated by the Hubble constant, which indicates the speed at which the universe is expanding. Anyway, estimations of the Hubble constant are not direct. Measuring the Hubble constant can be broadly arranged into two gatherings: nearby estimations and early universe estimations. Nearby estimations involve the investigation of the galactic clusters of the universe. For instance, Cepheid variable stars and Type Ia supernovae act as standard candles to measure the Hubble constant. Because of their brightness, astronomers can measure how the universe's expansion affects the rates of these objects to determine their distances and thus calculate the Hubble constant. The second group is the estimation of the early universe. Researchers use perceptions of the cosmic microwave background radiation (CMB), the glimmer of the enormous bang found in the 1960s. The CMB showed the microwave radiation of the early universe when it was only 380,000 years old. By measuring the small temperature and polarization fluctuations emitted by the CMB, space experts can lay out the age of the universe and its rate of development. Yet here's the issue. The consequences of these two strategies don't correspond. The outcome observed through nearby estimations confirms that the universe is expanding faster than what we estimate based on CMB data. Because of these differences, researchers have been endeavoring to uncover the reason behind the outcomes. As such, further research is being conducted to learn more about the secrets of the universe. As things stand, the difference in estimations shows that there is either new science we have close to zero familiarity with or errors in one or both ways by which we are measuring things. Because of the James Webb Space Telescope, we can see into the dark universe more clearly than ever before. The telescope can show the slightest and most distant components, planets, and galaxies we wouldn't have thought it was feasible to see. Due to its capabilities, researchers naturally assumed that data from the JWST would help us in accurately calculating the Hubble constant. Anyway, the first wave of data has surprisingly made matters more complicated. They have provided us with new insights that are not coherent with what we assumed we knew. Might this information lead to a new theory and alter how we contemplate space? Provided that this is true, we might have to review our understanding of how the universe works. For example, we may find particles and forces that have never been noticed, or it could mean that dark energy, an unexplored world factor responsible for the accelerating expansion of our universe, should be reconsidered. Up until this point, the ways we think about space have evolved as we continue to discover new things. For instance, in 1965, when scientists found the cosmic microwave background radiation, it served as strong support for the idea of the theory of the prehistoric cosmic detonation. Before then, researchers felt that the universe was timeless and thus continually expanding at a uniform rate. Yet the new evidence demonstrated that was not true. Additionally, when we found out towards the end of the 1990s that the universe was ceaselessly expanding, we discovered dark energy and its effect on the universe's development. In this way, every time we learn something new, we question whether it fits into our ongoing framework. If not, we come up with new ways to comprehend the universe better. To this end, the issue we are facing in cosmology today could prompt the discovery of the most awesome answer for the universe. While the issue is challenging, it is also elating as it forces us to develop more technologically advanced tools to explore space. This cosmological situation likewise unites the logical community from various nations, as each researcher wants to learn more about the universe. In particular, it shows that science is continually changing and developing as we more deeply study space. Alongside the Hubble pressure, there is likewise a concern known as the S8 pressure. This is regarding the spatial dissemination of matter in the universe. This can be utilized to draw a structural image of the universe and perceive how it has developed. Space experts refer to this peculiarity as unevenness, since there are areas of space that have bunches of galaxies closely grouped while different regions are scanty. Specialists additionally utilize the cosmic microwave background, CMB, and radiation from the outset of the enormous detonation. This light has been in motion for around 13.8 billion years, bearing news from the early universe. Through CMB investigation, physicists can unravel how the universe was uneven in its birth, which should match the observational lumpiness of the universe right now on a large scale. Yet here's the catch. These results additionally don't align. The CMB's lumpiness, as presented by the non-round gravity distribution model, implies that the matter distribution at the early stage of the universe was more homogeneous compared to the one observed using gravitational lensing. As such, we can figure that there is something else we are not considering in the explanation. This takes us back to the idea of dark matter. What precisely is dark matter, and how does it work? The truth is, this question remains unanswered. Anyway, all hope isn't lost, as the James Webb Space Telescope, JWST, is set to reclassify the field of cosmology with its remarkable high resolution and camera sensitivity. The telescope will examine early periods of the universe and research the principal galaxies and stars formed. This makes it conceivable to improve estimations of cosmic expansion and matter distribution. These basic inquiries will require exact perception and possibly new approaches from a theoretical perspective to figure them out. Whether the conclusion is giving more significance to dark energy, discovering totally new physics, or even gaining a better comprehension of dark matter's behavior, the implications will be far-reaching. Handling the secrets of the universe is like sorting out a zillion-piece puzzle blindfolded. Researchers should be viewed as careful investigators who are focused on and fixated on solving these mysteries. The latest endeavor, called Project Flamingo, is proof of NASA's heightening energy for logical exploration. Utilizing one of the world's most exceptionally acclaimed supercomputers arranged at Durham College in England, Project Flamingo is a totally fantastic accomplishment in the realm of computational advancement. It costs more than 50 million hours of PC time and features 30,000 cycles and counting. The operation highlights the academic community's goal to explore the universe fully, significantly zeroing in on dark matter. Dark matter, the baffling substance that neither radiates, absorbs, nor reflects light, is gathered to exist because of its gravitational impact on visible matter. Its elusive nature continues to interest researchers. Anyway, the methodology of Project Flamingo is not quite the same as past simulations. It involves all possible types of cosmic components, from galaxies of the most diverse gas content to stars and black holes at the center of the universe. Through such an organized approach, the gradual transformation in the portrayal of the universe was created from an essential landmark sketch. The inspiration behind ambitious undertakings like Project Flamingo is clear: to explain cosmic conflicts where the estimations seem flawed and do not fit into the structure of the universe. This uniqueness in estimation suggests a fundamental misunderstanding in our current comprehension of the universe's activities. In the event that these measurements can be compared to musical classifications, they are like jazz and classical, each having its own method, albeit still related. Flamingo endeavors to combine these dissimilar perspectives and hone our individual view of the universe. Anyway, regardless of its refinement, the cosmic pressure persists. This strain continues to exist as sobering proof that we have yet to address a significant part of the mystery that surrounds us. The universe appears reluctant to exchange its secrets with us just like that. As we add each new data point and simulation model to our toolkit, like Flamingo, An increasingly vast new universe opens up with new problems to solve. This is a never-ending mission where each answer prompts